Good afternoon. Today I'd like to talk with you about the final aspect of op-amps that we need to cover for the semester. That has to do with different kinds of feedback connections other than the negative feedback connection, which we've been using to force the operational amplifier to stay in the linear region, and in so doing, enable us to be able to wire up the operational amplifier as a linear amplifier to get some gain on whether we have an input voltage or an input current, however the case might be. So let's start by considering what would happen if we just operated the op-amp without having any feedback at all. This is the topology that's shown on the current slide, where we have two inputs, V minus and V plus. And in this case, the output is just directly going to be whatever the open loop gain A is times the difference between the two inputs. However, because A is so large, it's usually on the order of 1 million or more, even for a very small difference in voltage between V plus and V minus, this circuit is going to saturate. And so we can summarize the behavior of this configuration by stating that if V plus is greater than V minus, we will have positive saturation and our output will be whatever is the positive supply voltage, VCC. And if our V minus is greater than V plus positive, then instead we would be going into negative saturation, in which case V out would be equal to VDD. So in this situation, the op-amp is essentially behaving as a comparator, which is a nifty little circuit to have. However, there is a disadvantage with this topology in that this topology is very sensitive to noise. And to show you where this sensitivity comes from, please consider the image to the right where we've shown a sine wave as being the input on one of the terminals, but a noisy sine wave. So it's not something that is going to cleanly transition voltage when being compared to V positive. And in particular, if you look up close at the interval over which the sine wave is just about the same value as V plus, you can see that because of the noise, it kind of jiggles around the value of V plus. So it'll come by initially being greater than V plus, it'll go down for a little bit, but then because of noise, it'll come up a little bit, and then it'll go down again. And as a result of this kind of wiggliness, there's going to be multiple crossings between V minus and V plus. And each time, the output is going to either get saturated on the positive side or on the negative side. And that's going to result in this kind of a glitching effect in the square wave. It's not going to be a clean compare, if you will. So one way that we can solve this problem is through the use of feedback, only this time instead of using negative feedback, we're going to be using positive feedback. Now, at first glance, it might seem that this is a bit odd, because if you think about what positive feedback does, is it essentially is continually driving your op-amp into saturation. To see this, consider a situation where you have a ball that's initially balanced on top of an inverted bowl. If this ball would always remain perfectly balanced on the bowl, then we would be in the linear region. However, in practice, if you have a perfectly smooth surface and there's very little friction, etc., this ball is going to roll to one side or the other. And what positive feedback is doing is essentially just speeding up this process. So when you have positive feedback, the op-amp is never, ever going to be in the linear region. It's always going to be saturated. The question is only whether it's going to be in positive saturation or negative saturation. We can use this mechanism to our advantage to design a glitch-free comparator. There are several potential alternative designs for this, but today what I would like to do is just go over one of the more ubiquitous and well-known designs, which is known as the Schmitt Trigger, which is shown here on this slide. So basically, if you take a look at this, you can see that we have positive feedback, because if we trace our output is getting tied back over R2, back into our input. So here's our positive feedback. And so we know, therefore, that the output is either going to be positive VCC or negative VCC in this case. So how do we characterize the behavior when we have this kind of connection, and how do we think about even how to analyze this circuit? So since we don't know where we're initially starting, we have to make an assumption. Okay, we have to assume that it's either in positive feedback, that it's either in positive saturation or in negative saturation. So if we are in positive saturation, then V out is going to be equal to positive VCC. And in this case, we can actually use this to generate a requirement on the relationship between the two inputs. So we're going to first find independent equations for V minus and V negative. In this case, V minus is going to be equal to just the voltage V in, and V plus is going to be equal to R1 divided by R1 plus R2 times V out. Note that because we're still assuming that the input resistance to the op-amp is infinite, the input currents being drawn are still zero. The only aspect of the ideal op-amp model which we're not using is the idea that V plus is equal to V minus, because that is only a condition that is relevant. Sorry about that. The reason for why we don't assume that V plus is equal to V minus is because if V plus had equaled V minus, then we would be in the linear region. In contrast, in this circuit, we're explicitly assuming that we're not in the linear region, that we're saturating. So the fact that I plus is equal to I minus is equal to 0 is still valid, but this is now going to be the only aspect of the ideal op-amp model that we continue to use or carry forward when we're analyzing this circuit. So getting back to these two input voltages we've defined, we can decide whether we're actually satisfying the conditions for positive saturation or not by basically substituting for V out, VCC, and saying that, well, if we want to stay in positive saturation, so to stay in positive saturation, we need to require that V plus remain to be greater than V minus. And so what this essentially means is that we would require R1 divided by R1 plus R2 times VCC to be greater than Vn. And as long as this is true, then our output is going to be equal to VCC. We can have a kind of similar kind of relationship if we think about what happens if V out is in negative saturation. So if we are in negative saturation, then the reverse should be true, right? We should want our V in to be greater than whatever V positive is, which is going to be R1 plus R2. But now instead of V out equal positive VCC, we're going to use the fact that in negative saturation, V out is equal to negative VCC. And so if you look at this, you can see that we've essentially defined two thresholds in this circuit. One is the voltage divided value that I've just highlighted in blue, which is a positive value. And the next is this value that I've just underlined, but that's going to be just the negative of the positive threshold that I've identified in the first case. So if I'd like to just kind of explain to you what the operation would be like graphically, I think things would be a little bit more clear. So let's look at how this circuit behaves in terms of its input and output transfer characteristics. So let me first label these two thresholds. So in one case, we have R1 divided by R1 plus R2 times VCC, which is a positive number, and hence I've put it to the right side. And then you have the negative of that, so negative R1 divided by R1 plus R2 times VCC, and that is on this side. Now, how does this circuit actually behave? Remember what the meanings of these voltages were. We said that in the first case, that if this threshold was always greater than V in, that we would be in positive saturation. So what is the region over which we are in positive saturation? Here's our threshold. The threshold should be greater. So basically any input which is less than that, as I'm indicating here, this should be the region where we're in positive saturation. And this value here is just going to be plus VCC, and this is going to go all the way back to minus infinity. And then once we've exceeded this threshold, we're going to go into negative saturation, and this is going to level off here as follows. So this is kind of one trajectory. where if we start from negative infinity and think about how it behaves when we cycle the input all the way to positive infinity, we're going to be following this red curve. But what happens if we're at negative saturation? Remember, what did we find for negative saturation? The input needed to always be bigger than the threshold, but the negative threshold to be in negative saturation. So we're actually dealing now with this blue curve here. So here's my threshold, and I'm always going to be in negative saturation when the voltage value is greater than that. And otherwise, I'm going to be in positive saturation. So you now have two curves. This is a kind of unique situation in circuits, which is called hysteresis. But what it allows us to do is it generates this buffer kind of in the middle here, where when we try to do the switching, we are now not going to get any glitching effects due to the fact that we now have this intermediate region, which is kind of a buffer on the decision of actually switching from positive to negative saturation. As an example, let's do the same sine wave that we had before when we were thinking about the comparator. And let me show you what would happen now differently when we have the Schmitt trigger. So let's plot on a time domain here what the voltage would be as a function of time. This is going to be our output. Well, we're going to plot the input and the output. So let's first plot our thresholds. So this is going to be our positive threshold, R1 divided by R1 plus R2 times VCC. And then we have a negative threshold here. So here's negative R1 divided by R1 plus R2 times VCC. And let me also now draw the sine wave that we had. So this will be a noisy sine wave. So let's say our sinusoid is, well, cosine wave. Let's say our noisy sine is doing something like this, just for argument's sake. And I should have drawn this a little bit more carefully so that I could show you what happens if you would otherwise have glitching. So let me try this again. So let's say you have something which went like this. And then it came up like this. Okay, and so forth. Now, here's the area where we had glitching before. Because of these three intersections, if we had a regular open loop configuration, we were getting glitching. But look what happens with the Schmitt trigger. So initially, because our negative input has a larger voltage value than our positive input, this circuit is going to start out in negative saturation. When we're in negative saturation, in order to get back to positive saturation, we need to have an input value that is lower than the value of the negative threshold. So this green voltage here is not going to go back into positive saturation until its value drops below the value of the negative threshold. And that first crossover point occurs right here. Once this drops below that value, which it does ever so slightly here, pardon my slightly bad drawing skills, but once it dips slightly below that threshold here, this circuit is going to go into positive saturation, and this voltage is going to pop up as such. Now, the voltage might fluctuate up and down around this negative threshold, but it's not going to be able to go back into negative saturation anymore because of that fluctuation, because now, once we're in positive saturation, we have a different threshold. And the new threshold is the positive threshold we have here. To go back into negative saturation, we require that the voltage levels are such that we now have an input which is greater than this positive threshold. So my drawing here is a little bit skewed. I don't know if it's going to kind of let me draw outside the slide. Hooray, it lets me do that. So when this increases again, as I've shown here, this is only going to go back into negative saturation once the green curve, again, exceeds the positive threshold, which is what we have here. And so at this point, it's going to go back into negative saturation. And once we're in negative saturation, we have to surpass the negative threshold. And so even if this voltage continues to oscillate across the positive threshold, it's not going to cause the circuit to flip back into a different mode of saturation. And so as a result, the Schmitt trigger does not exhibit this kind of a glitching effect that you normally have with the regular comparator. Of course, the operation of a Schmitt trigger is slightly different as a comparator, because now instead of having just one threshold, you have two thresholds. However, you can try to design the ratios of this R1 divided by R1 plus R2 such that they're not very far apart, and only have them spaced enough so that you're far enough apart from the noise, so that every time you have a noisy signal, you don't get any kind of flip-flopping back and forth. So this is one of the common, or maybe the most common, positive feedback op-amp circuit that's out there, which is used for a variety of reasons. Note that one of the other possible applications of the Schmitt trigger is as a square wave generator, because you can now use the adjustment of the thresholds to determine what your duty cycle on the square wave is. But again, this is just as a different example to show you what happens, and also to make you aware of the feedback, so that you can make sure when you're analyzing op-amp circuits in general, you first check for the feedback and then decide the type of analysis you're going to go about doing. If you have any questions, please contact me and let me know. Otherwise, I'll see you all in the next class. Take care. Bye-bye.